All right, y'all, here we go. So, guys, what we need to do is we need to lay a conceptual framework for what we're about to do. And then we're going to go to Math Magic Land. And we are going to thumb our proverbial noses at the quadratic formula. Be gone, evil quadratic formula. John, don't make me talk to you about logarithms. Those are less fun. But guys, with that said, let's lay the groundwork, shall we? Worth writing down. I think so. Guys, this is worth writing down. So first of all, this is sort of where we are right... Oh, nope, didn't want to do that. Sorry. So guys, this is where we are right now. If we have a 1 liter beaker with water in it, we know that its pH is 7. But then, guys, as we think about that beaker of water with the pH of 7, I'm going to spice things up a little bit because we always use HCl. We're going nitric acid, y'all.
Yeah.
Oh, yeah. It doesn't matter. Guys, whatever acid we dump into this water, guys, this completely does its thing, right? It protonates. We know that because it's one of the 7. It's a strong acid. And so, guys, when we look at this solution, disregarding the water, we've got nitrate. And we're not going to include the water in this picture. Guys, what's the molarity of nitrate in this solution? 1 molar, right? 1 mole in 1 liter. And then, guys, we've got protons. Please understand that we know that those protons are actually hooked up with water to form hydronium. But guys, what is the molarity of the hydrogen ions? 1 molar. Technically, we understand that it's 1.00000001 because there's already some protons. John, you got to stop that. Guys, there are protons already in solution because of the autoionization of water. But guys, that little bit of proton that was there originally is a rounding error. And so what if we then wanted to find the pH of this solution? Go, John. What do? Logarithms. How? Yeah, pH is equal to... Guys, you need to know the backstory. John came in last night with his dad, and we had a logarithm moment. Logarithm moments are never pretty. So, guys, we're simply going to do this, right? The negative log of 1. So it's 10 to the negative... Yeah, and you guys understand that. To solve it, it's actually 10 to the negative 1, which is... Oh, sorry. Wait. What is it?
10 to the 0 is 1.
10 to the 0 is 1.
It's like 1 over 10.
It's 10, right?
It's 1 over 10.
John, help us. Do a logarithm. My brain is fried after...
0.1. I think the negative exponent flips it.
Yeah. Negative exponent.
So it's 0.1.
Yeah.
Yes.
Ah, thank goodness. All right. You guys get the idea? Now I need to draw another beaker with you. Ah, yeah. 1 liter, 1 mole. Question for you. Knowing that you guys have spent countless hours skipping practices, skipping social functions, surrendering sleep, memorizing the strong acids again.
Among many other things.
Guys, how many of the strong acids only have 1 hydrogen? There's 7. How many only have 1? 6. There's one that has, There's one that has 2 hydrogens. H2SO4. Guys, we haven't talked about this before, but we need to do this now. Guys, H2SO4 is what is called a polyprotic acid. Poly meaning many. Specifically, we would call it diprotic, but we need to think about how to think about this. So, guys, if we put 1 mole of sulfuric acid into water, guys, what's going to happen? So, sulfuric acid is an acid, yes? Yes. And it's one of the strong acids. So guys, please complete the equation. If H2SO4 is a strong acid, what does it do? So what do acids do? Well, they give away hydrogens. So guys, H2SO4 gives away a hydrogen, so we end up with protons, and we end up with bisulfate ion. Yeah? But guys, here's the trick. H2SO4 still has a proton, and it can give it away. So did I say H2? Yeah. Sorry, HSO4, the -1 charge, still has a proton. Please write the equation that represents the bisulfate. Can I say bisulfate? You know that game, right? If there's a hydrogen stuck to an ion, you add. So if SO4 minus 2 is sulfate, with a hydrogen on it is bisulfate. So guys, write the equation that represents the bisulfate ion functioning as an acid. So we get another hydrogen, another proton, and then we end up with SO4. But now, guys, let's clean up our mess. What is the charge of SO4? -2. But, guys, we still have a problem. It reaches equilibrium. HSO4 bisulfate is not a strong acid. You know that. It's not one of the 7. Consequently, it reaches equilibrium. So now, guys, the $11,000 question is, if you've got a bucket of battery acid, because that's what sulfuric acid is, if you've got a bucket of battery acid, what's in there? Let's not include the water. But guys, in your beaker, please identify the species that exist in solution. Guys, okay? All right, so let's talk. Is there any H2SO4 in solution? No. It's a strong electrolyte. It completely it's a strong acid. This be gone. So guys, do we have any protons in solution? No. Oh yeah. With the understanding that they're really hydronium, but we can simplify. Now guys, do we have any bisulfate ion in solution? Yeah. We do. So guys, we've got some of that. Is that it? No. Because this bisulfate can also break apart. Guys, when this breaks apart, what do we end up with? We end up with more hydrogen ion, and then we end up with sulfate. Now guys, what I need you to do down below your beaker is put them in order. Which one has the highest molarity? Which one has the lowest molarity? And which one's in between? If this question frustrates you, it should.
The icebox.
Maybe. So guys, let's talk about the clear winner, and then let's talk about the part that's fuzzy. Which one is there the most of?
H+.
This guy? That's why sulfuric acid is so icky, yucky, bad. Because, guys, this is a 1 molar solution. Don't miss this. This is a 1 molar. If you were to pick up this bottle, it would say 1 molar H2SO4. But guys, understand there's more than 1 molar hydrogen ion. Because when we label bottles by molarity, it's solute divided by salt solution. And guys, we put a mole into a liter. But the concentration of hydrogen ion is greater than 1 because we get more protons from the second protonation. Does that make sense? Okay. So guys, with that said, the question then becomes, how much of this do we have and how much of this do we have? Not the pH. Guys, what we need to know is the Kc value for this equilibria. If the equilibria lies strongly to the right, we would have more SO4 minus. Yes, minus 2. If the equilibria lies to the left, right, smaller or larger than 1, then it would be more of the H2SO4. Now, and with Michael or Kale, one of you, it was cool that you came up with this. Guys, to answer this question, what we need is we need to do an ice box. But when we do this ice box for weak acids, we don't call it Kc, we call it Ka. Guys, grab your equation sheets. So guys, looking at your equation sheets, guys, this is the generic form of what a weak acid does in water. We don't include the water in the process. We understand it's there. Water is a reactant. Hydronium ion is actually the product. But guys, if we write the Kc for this, that was not Kc. I was thinking about the acid again. Guys, when we write the Kc for this, we've got this. Now guys, the question is, do any of these not belong in the expression because they're liquids, pure liquids or pure solids? They're all dissolved in water. And guys, if you don't understand what I'm talking about, go back to here. This is dissolved in water, this is dissolved in water, and this is dissolved in water. This is our HA, this is our H+, this is our A-, our conjugate base. And guys, all of these are dissolved in water. They all have molarities. And as a result, they all belong in the statement, and it looks like this, which is conveniently located on your AP sheet. Got it there? Okay, so guys, a couple thoughts. When you're solving these on the test, you do not need to write that down. I know that we talk about writing down the equation, then filling it in, because you don't have to identify this. What you would have to identify, given our previous example, would be SO4 minus 2, protons, and HSO4 minus 1. That's what you would need to do. You don't have to go all the way back here to this generic form, okay? One other thing. Guys, when you write the chemistry of weak reactions, weak acids and bases, it doesn't matter which one of these you put first. Get in the habit of putting the conjugate base first. You'll thank me in 2 weeks. Guys, get in the habit of writing your conjugate base first. Yeah, it doesn't matter. But guys, I've got a way of teaching you buffer chemistry that is going to make you a demigod when you get to college. And it all hangs around the idea that you put the conjugate base first. It makes it so much easier. So guys, just trust me, get in the habit. You guys good? Good foundation? We're going to solve 2 problems and call it a day. You ready? John. Sometimes I feel like I scare you.
That's not bad.
I know, right? All right, so guys, can we agree with these ideas? That weak acids are all but the 7. They don't completely protonate. They reach equilibrium. And guys, we've got this HA expression, which is like Kc. It's on the AP equation sheet. And we're going to talk not about Kcs. We're going to talk about Kas. And guys, the idea with Ka is that we've got Ka is equal to A minus, H plus, and unprotonated HA. And the idea is the larger the value of Ka, the more it breaks apart and the stronger the weak acid is. Yo? You okay? Okay. Then guys, briefly this by way of review. Let me clean this up, and this is going to freak out, but we're coming back, and here we go. So guys, let's do this thing. So it says this: a student prepares a 0.1 molar formic acid solution. If the pH of this solution is 2.38, what is the Ka for the formic acid? And then guys, the next question is this: what percentage of the acid is protonated? Guys, I'm not going to turn you loose on any of these. Guys, we are going to solve all of these together. So if you want to write down the question, you can. I don't think it's really that necessary. But guys, we're going to solve this. So we now have a weak acid. This is called formic acid. How do you know formic acid is a weak acid? Because it's not strong. By the way, guys, formic acid is ant spit. Yeah, so this is actually the acid that ants produce. They have glands that create formic acid in the same way that we have glands that create hydrochloric acid, which is our stomach acid. Formic acid is actually the acid that ants produce. And so I think you know this, ants don't sting, they bite. But when they bite, they're actually injecting formic acid into the wound. And that's why ant bites sting so badly. It's because they're actually injecting you with formic acid. Anyway, so guys, I know, right? As if you didn't have already a reason to hate ants. So, guys, the question is this. We make a 0.1 molar. Can you picture that? A 0.1 molar solution of formic acid. By the way, guys, interestingly, all weak acids are crystals when they're not dissolved in water. Vinegar, it's a crystal. Guys, formic acid, lactic acid, all weak acids are crystals in their molecular state. What are all the strong acids in their molecular state? Gases, good. Okay. So guys, it says this: if the pH is 2.38, what is the Ka for formic acid? So guys, let's stop there and answer this question. So guys, when you picture Ka, where are we headed? What do we need to know in order to solve for Ka? So guys, when you get this question on the AP test, and you're going, oh crap, I don't know what to do, and you understand the first thing you've got to do is do something, right? So you grab your AP equation sheet, and you look for Ka. And when you find it, what do you need to know in order to solve for Ka? You need to know conjugates. But what do you need to know about those things? What values satisfy that Ka expression? Molarities. So guys, what we need to know is we need to know the molarity of the acid, we need to know the molarity of the conjugate base, and we need to know the molarity of the hydrogen ion. This starts to feel a little iceboxy. If it doesn't, it should. But guys, here's the trick. Nowhere in this calculation does 0.1 molar satisfy any part of the Ka expression. Let's talk about why. Don't draw this. So guys, we are going to create a 0.1 molar, we're just going to call it Form H. We're going to create a 0.1 molar Form H solution. Guys, it doesn't even matter if we know what the conjugate base for formic acid is. We don't care. We just need to know we've got an acid and a conjugate base. So guys, when we put formic acid, Form A, in water, this crystalline salt dissolves in water. But what does that salt do? It's a weak base or a weak acid. What does it do? It breaks apart. It reaches equilibrium. So some of these hydrogen ions go away weakly, but some of these hydrogen ions go away. They hook up with water and form hydronium ion. And guys, when they do, they also then form a conjugate base, which we're just going to call form negative. That's the conjugate base. Now guys, here's the trick. What are the concentrations of all of these things in solution relative to 0.1 molar? Go ahead.
Concentration of hydrogen and form
No. Talk to the person next to you, guys. What are the concentrations of all of these things in solution relative to 0.1 molar? Talk about it.
But if it breaks apart, like if one becomes apart. Well, it breaks apart. So we're saying the total they add up. No, they don't. Like they don't because it's one on one side. You bring one in.
Walk away from the idea of add up.
Hold on.
Yeah.
Break it apart. Is it like the other ones? Like it breaks apart 1 molar. Is this 1 molar of that?
But it's not 1 molar, 0.1 molar. Okay, guys, let's talk about what the answer isn't. Guys, the answer to this question, and I'm going to write it over here, Form H in equilibrium with Form minus and H plus. Guys, the answer, so the question we're asking is molarity of each one of these. And guys, the answer to none of these is 0.1 molar. None of these are 0.1 molar in solution. Why not?
Because they don't break apart entirely.
Right, because guys, the maximum molarity would be 0.1 molar. So imagine that this is a strong acid. It's not. But guys, imagine if this was a strong acid. How much of this would there be? None. It would obviously be a single-headed arrow. There would be none of this, and so this would be 0, and what would these molarities be? 0.1 and 0.1. But this is a weak acid, so that's not what happens. So what is the concentration going to be if this reaches equilibrium? Somewhere below 0.1. So this is going to be less than 0.1 molar. We don't know how much less than. We're going to talk about that in a minute. But it's less than 0.1 molar. So it's somewhere between none, which would make it a strong acid, and all of it, which would make it a non-electrolyte. Know what I'm saying? Now this. What do we know about the concentrations of these? They will be the same. Okay? I know that Jared and John, you guys were playing with the add up idea. I want to chase that in a minute. But guys, for right now, we just need to understand that these will be equal. Is that okay? Now imagine this. Imagine that we could measure the concentration of hydrogen ion. And let's just say it's some X. Then guys, what would the concentration of this be? Also X. And guys, what would the concentration of this be? 0.1 minus X. Now guys, if only there were a way that we could measure the concentration of this, John. Not an icebox. pH. See guys, if we know the pH, then we know the concentration of this. And guys, check this out. We just made an ice box. That's how to solve this thing. So guys, let's do it together. You ready? Where's my pointy thing? And back here. And I'm going to grab, no, back here. Go away. I hate you. Sorry, was that strong? My bad. Jonah's been working with me on strong language, mostly by subjecting me to it. And so guys, let's go slow and let's do this purposefully. This is an ice box, but trust me on this. If you'll structure it the way that I do, this is going to make one of the hardest things that you're going to learn in this class really accessible. So let's get started. So guys, our weak electrolyte is HCHO2. Then leave yourself good space in equilibrium with. Now guys, I'm just going to call it hydrogen 1, the one on the left, or hydrogen 3, the one in the, it's really hydrogen 2, but it's the third thing. Guys, which is our acidic hydrogen? Hydrogen 1 or hydrogen in the middle? So the trick is this. Guys, when we write acids and bases, we always write our acidic proton either first or last. That's the rule. So we write our acidic proton first or last. Don't worry about the Lewis dot structures. Don't worry about the idea that that hydrogen is somehow strangely associated with the oxygens. Guys, we just go like this. Leave yourself some space. CHO2. Sorry. And protons. Guys, again, A plus B, B plus A doesn't matter. Put the conjugate base first. Trust me. Okay. Now, guys, ice this thing. So let's look at what we know. What is the initial concentration of the formic acid? Yep. I'm going to just be really sloppy with digits and units. 0.1 molar. What is the initial concentration of both the conjugate base and the protons? 0. Now guys, as this then falls to equilibrium, what happens to the amount of unprotonated formic acid molecules? Goes down. How much? We don't know. Let's call it X. But guys, here's the trick. I wanted to do that to tie this back to the way we just talked about this. I think that Michael did the math. We actually do know how much it changed. We don't have to call it X. How do we know? And guys, the answer is this. We know this. We know the hydrogen ion concentration at equilibria. How do we know it? We know the pH. So guys, and you need to show this calculation. You can't skip this. pH is equal to the negative log, I'm just going to call it X. What is the pH? 2.38. So I'm just going to say X is equal to 10 to the negative 2.38. Has somebody already done that math? Did you do it?
It's 0.0958.
No, that's good.
Boy, this is a tough audience. So 2.38.
That was so mean.
Oh, I did 0.1 minus that. Oops. It's 0.00 what? 4-1? Yeah. That was the one.
Let's call it 4.2.
1 minus that.
So 0.0042. So guys, if that is 0.0042, that means this went up by 0.0042. But guess what happened to the conjugate base? Also up by 0.0042. So this is 0.0042. But now guys, this goes down. My voice just changed. By 0.0042. So we have 0.1 minus 0.0042. And again, being probably inappropriate, I'll do better. 0.0958. At the risk of getting jumped on like y'all did to Michael. Did I do that math right?
Yes.
Okay.
That was so mean.
I know.
Everyone's like, no.
Bad. No. Stupid head. All right, so guys, then this. Ka is equal to, this is what this calculation needs to look like. Am I okay this low on the board? Like, Garrett, can you, is that okay? Am I all right? Okay. So guys, we've got CHO2 minus, and then guys, yeah, I'll write it out. Hydrogen ions, and then guys, HCHO2. Is that okay? It's hard for me to write down low. You okay? Then guys, what if I do this? 0.0042 squared divided by 0.0958. Is that sitting okay? Ooh. 1.8 times 10 to the negative 1, 2, 3, 4. Yeah, and John, I know I'm not being a good example, but you should be putting units on your numbers. I'm not, because I'm trying my best to get this to fit on one screen. Yeah. So guys, can we confirm or refute 1.8 times 10 to the negative 4th?
Yes.
Is that okay? Okay, now let's talk about what that means. Does the equilibria for this weak acid lie to the left or to the right? So it's smaller than 1, right? So guys, if the value is smaller than 1, which one predominates? The denominator or the numerator? The denominator, which means at equilibrium, there's a lot more unprotonated acid than there is hydrogen ions and conjugate base ions. Thank goodness. Because if the equilibrium lied to the other sides, ants would be a whole nother set of problems. Do you see what I'm saying? Okay. So guys, this then leads us, and we need to pause. Questions or thoughts about what we just did? You okay? Now go, please. Good question. So guys, remember, you're talking about this, right? Guys, remember that Ka is a dimensionless number. It doesn't have units. It's simply a value that represents the relative ratio of reactants, products to reactants at equilibrium. So there are no units. You guys okay? Okay, now guys, remember on the AP test, there's a couple calculations that the AP people expect you to be able to do without an equation, right? What are those calculations? Things like percent error. Here's another one. You want to write this down. Percent protonation is equal to concentration hydrogen ion divided by concentration of HAC. So guys, in our example, this would be the concentration of hydrogen ion divided by the concentration. And guys, this is concentration initial. So guys, reaching backwards into the previous example, so our concentration of hydrogen ion is 0.0042 molar, and then our initial concentration of the acid was 0.1. So guys, stop and think with me so you don't have to memorize this. What does percent protonation represent? It represents how much acid was available to break apart compared to how much acid did break apart. Okay? So guys, with those numbers, we're going to go 0.0042 molar divided by 0.1 molar, and then we'll multiply that by 100 to turn that into a percentage. And guys, when you do that math, 4.2%, right?
Yeah.
So guys, here's what we're going to do. For argument's sake, just to talk about this, let's call it 4%. So guys, if that number is 4%, here's what that means. Ant spit is 96% unprotonated acid. It's dissolved in the ant spit, but it is not protonated. So all of the formic acid that those ants produce, only 4% of that acid actually breaks apart and turns into Bernie stuff, the protons. Guys, 96% of the molecules that ant makes dissolves into water, but it doesn't protonate. That's what percent protonation means. Yeah.
What about the percent of CH of your member?
It would be the same. Yeah, so it would be 4% this and 4% that. They're the same.
That's 96.
But it's not, yeah, so the way we think about it is 96% of the acid hasn't protonated. But what we actually talk about is we would say, because this is the percent unprotonated.
So 96% doesn't burn you, 4% does.
Correct, exactly. And that's the part we talk about. We say this is 4% protonated. Is that okay? Yeah.
So if it was backwards, does that mean that 96% would burn?
Yeah, and that would be bad. Like, if you think about it, acids, guys, put this on for size. Acids protonate 100%. Strong acids protonate 100%, right? So if it was 96%, you're on the cusp of being a strong acid. That would be a mess. Yeah, go ahead.
But how do you treat the ant acid and as you try to neutralize it? So we start with 4% being active, and then you neutralize it with not relative 4% relatively build back up.
You'd have a little Le Chatelier's principle going on, but let's just say 4%.
Okay.
All right? Okay, so guys, we got one more problem to solve. This is actually pretty darn fun to teach. This is sort of magic. So let me do this. Let me look at how we can cleanly transition into this. Okay, let's do it. We're just going to leave it here and do it. So guys, it says this. What is the pH of 0.3 molar vinegar? Guys, if you're looking at this and you're going like, I get ice boxes. I know what I'm doing. Guys, please, this is important. The question that we're now asking, which is relatively, I think, non-threatening until we get into it, is what is the pH of a 0.3 molar vinegar solution? So guys, doing this with me, the first thing we're going to do is we're going to write down our weak electrolyte, the vinegar. Then, gang, I want to give myself a little more space. Then, giving ourselves space, it's a weak acid. Now, guys, what are we going to put first, the hydrogens or the acetates?
The acetates.
The acetates. Always conjugate base first, and then our protons. Because I don't know why I love teaching this part. This is pretty cool. You're going to like it. Okay. Now we need an ice box. And I'm going to make it relatively short, just because I want space to be able to play with this with you. So now let's populate our ice box. This is 0.3 molar. Again, guys, forgive my sloppiness with units and significant digits. Now, guys, what about the acetate and the protons initially? 0. Okay.
Units if it's like 0.
Doesn't matter. Now, guys, this. What are we solving for? pH. So where in this ice box is something about pH represented? And the answer is down. I'm trying to do this so it all lines up. Guys, this is where we're headed. In the previous question, can I get to it? In the previous question, we were given the pH, which gave us that, which then allowed us to populate the rest of the box. In this question, we are solving for that. And so, guys, as a result, we've got to make some assumptions. So, when this acetic acid goes into water, what happens to this? Some of it breaks apart. How much? We don't know. What are we going to call it? X. So this is minus X. But then, guys, if that goes down by X, what happens to these? They go up by X. And when we bring those down, I'm going to just completely... Oh, no, I'm not. I'm going to get rid of my line. Guys, this is X, and this is 0.3 minus X. So now, guys, let's write our Ka expression. Ka is equal to the concentration of acetate, protons, unprotonated acetic acid. Because I need to think about this. I think I'm going to work to the right. I was thinking about working... So what would happen if I worked down... No, you know what? I'm going to take the first... Guys, is this okay for me to work down here?
Yeah.
I'm going to take the first step down, and then I'm going to work to the right. So, guys, let's be... Sorry, I was about to put thoughts in your head. What are we really solving for? X, which is hydrogen ion, which then becomes the pH. So, guys, to do this, if we're going to solve for X, we need to populate this entire thing. Notice that they gave us the Ka value. Are you guys really sure I'm okay down here?
Yeah.
Okay, so 1.8 times 10 to the negative fifth is equal to the CH3OA, the acetate and the protons are both X's. So are you okay if I do that? And then, guys, our denominator is 0.3 minus X. So now you're all grabbing for your calculators as you're trying to put this in standard form where you've got an x squared and x and another value, and then you plug it into the quadratic formula, right? That's what we would need to do to solve this. But guys, check this out. We can avoid that. And we can avoid this in ways that don't significantly change our answer, but radically change the complexity of the solving process. Guys, don't miss the logic. What does X represent? The change. Tell me more about change.
Concentration.
So where is that change flowing from? What's happening to the vinegar? It's breaking apart. And it's forming these bits, these pieces, right? Now, guys, let's talk about this. how much does that happen for this weak acid? What information would we need to know the extent to which this breaks apart? The Ka value. And you'll notice that we've got that Ka value. What does it tell us that the value is on the order of 10 to the negative fifth? Does it break apart very much? No, and if you're not sure, let's look at this. Guys, this is ant spit. Ant spit broke apart 4%. And what's its Ka value? It's on the order of 10 to the negative fourth. So if we have a weak acid that is on the order of 10 to the negative fifth, it is a power of 10 weaker, and consequently, using round numbers, we might think that vinegar only breaks apart about 0.4%. Know what I'm saying? Does that No. Does that logic make sense? I'm not tricking you. That's the logic. Does that make sense? So guys, if we've got a weak acid that has a Ka value on the order of 10 to the negative fourth, and if it only breaks apart about 4%, then guys, if we are looking at a weak acid that has a Ka value on the order of 10 to the negative fifth, it's going to break down even less than 4%. Does that make sense? Do you understand that logic? Because look at what it allows us to do. It allows us to get rid of this. Guys, what does that minus X represent? How much the weak acid breaks apart. Right? We started with 0.3 molar and it broke apart some X. But guys, using the Ka value as a guide, we know that the Ka is small. That means that this equilibria lies hugely in this direction, which tells us that not very much of this is going to break apart, especially compared to all that we had to start with, which is 0.3 molar. And so guys, because the amount that this breaks apart is so small, it actually becomes a rounding error in our math. And because it's a rounding error in our math, we just get rid of it. And now guys, this becomes the easiest question on the planet to solve. Where's my calculator? So guys, all we've got to do it with me, is go 1.8 times 10 to the negative fifth, multiply that by 0.3. I'm not even going to write it down because we can do math, right? So guys, we're going to multiply these together, and then what do we do to solve for x once we've multiplied that times that? Take the square root. And so if I take the square root of this, guys, this is 0.0023 molar. Again, I wish you guys spent as much time thinking about where to put stuff on paper when you took your tests as I do as I'm trying to. So let's think, where would this fit well? We're not done, right? What is that value right there? It's X. But what are we solving for? pH. So guys, I know this is really pushing boundaries. Can I work even still at the bottom of the page? Can you imagine that we're just going to go pH is equal to the negative log of hydrogen ion concentration is equal to the negative log of 0.0023 is equal to log, change the sign, 2.63. And that's the pH. You guys okay? You guys see it? Oh, and I should actually mention this to you. I need to show you how to officially represent that. I scribbled it out, but I didn't officially show you. Are you guys, I just need to show you the way that we represent what we just did. Were you okay with all the concepts? Was that okay? Okay, guys, let me just show you. Do you understand why we got to get rid of that X? Yeah. Let me show you actually how to represent it. The way that you actually represent it is this. What you do is you go, is approximately equal to x squared divided by 0.3, and then you solve that. Did that make sense? It used to be that you had to write a sentence. You had to write a sentence in the middle of your solution and say, I'm disregarding the change represented by x because it's so insignificant compared to the initial concentration. Now they just let us go approximately equal to. Yeah?
What's the range of Ka values that you're allowed to just cut?
Yeah.
Oh, sure. Steal my next question. Let's talk about it. Yeah, so guys, Michael's question, let's couch it for a minute because I want to lead people to that because you're going to hate the answer. All right. So guys, do this with me, would you? Let's do percent ionization. So percent protonation, percent protonation is equal to hydrogen ion divided by the initial molarity. You know what? We don't need to write the general form. Hydrogen ion divided by the initial concentration of CH3COOH. That is then equal to 0.0023 divided by 0.3 times 100. 0.0023 divided by 0.3 times 100. Michael got 0.77, is he right? Actually, I got that, but I wanted you guys to yell at Michael. Is it 0.77? Okay.
Now you just build my confidence back up.
You're good at math. Guys, we're going to bleed 2 minutes into break. So guys, let's think about this logically. You ready? Why did we get rid of X? Because it was insignificant. It was insignificant. Stop. And that tone actually hits a resonance frequency within my brain, and it just goes, ah! And I'm like, no. Thank you, Eleanor. So, guys, again, the logic. Why were we able to get rid of X? Because it's insignificant compared to what? The initial concentration. What led us to the idea that this might be okay? And guys, we talked about the idea that the Ka value is 1 times 10 to the negative fifth, which told us that the equilibrium lies largely to the left, meaning not much of this breaks up, and therefore we can get rid of this because it's insignificant. But guys, then we need the proof of this. And the proof is actually right here. Let's call it 0.8. Guys, in vinegar, this is 0.8% broke apart, and 99.2% ain't broke apart. And guys, if only 0.8% of this breaks apart, then that is insignificant compared to 0.3. Does that make sense? Because now, guys, the logic becomes cyclical. Because Michael asked the question, where's the limit? Right? How strong, let's put this in practical terms, how strong does a weak acid need to be before getting rid of this is no longer appropriate? Let's say that again. How strong does a weak acid need to be in order for this to not be appropriate? Do you understand the question? And guys, this is where we run into problems. The answer is actually based on percent protonation. Do you see the problem? Guys, if you don't understand the problem is this. To come up with percent protonation, technically you shouldn't get rid of this. Then you solve for percent protonation, and if you find out that it's smaller than some threshold, then you just come back and go, oh gosh, it would have been okay for us to get rid of the minus x, but we already solved it without getting rid of the minus x, and therefore we've already done the math, so never mind. So what do? And guys, the answer is this. We actually establish a threshold built on Ka. And guys, the threshold is this. If an acid is less than 5% ionized, it's okay to disregard the change represented by X. But guys, you understand that that does us no good, because in order to figure out the 5%, we got to do the math using the quadratic formula, and that doesn't do us any good. So we do this. Oh shoot, it wasn't there. Where did it go? Sorry, why is it not in the notes? Sorry guys, let me show you. I guess I just meant to write it down. I thought I put it in the notes. Guys, it's this. 1 times 10 to the negative third. Ka is equal to. Actually, let's do this differently. That's why I didn't do it, because it makes more sense to do this. Put it in the middle. This is our Ka value. Guys, if your Ka value is larger than 10 to the negative third, that is too strong a weak acid, and you can't get rid of X. Just a second. If your Ka value is smaller than this, then you're okay to get rid of the X. Are you going to ask, what if it is 10 to the negative third? So let's, guys, did you get this down? You okay? Does it make sense? Here's the answer. I can't think of the last time I've seen a question on the AP test where the Ka value was 10 to the negative third. The bottom line is this. If it is 10 to the negative third, 1, that sucks. But 2, don't drop the X. Yeah, 10 to the negative third is skating on that line. Don't mess with it. Typically, the Kas that you're going to see are like 10 to the negative 8th and smaller. They typically don't play that game with you. But if you see a 10 to the negative third, second, or first, quadratic formula. Yeah.
Is it ever super big?
No, because if it was super big, it'd be a strong acid. And so it would be approaching the behavior of a strong acid. So the answer to your question actually has a bigger context, because what you're going to see is most of the time when we're iceboxing weak acids and weak bases, it's going to be leading towards something about buffers, which you don't understand yet. But what you're going to find out is that when we build buffers, they're always built on weak acids and bases, and so you won't see the stronger weak acids and bases because they don't make good buffers, and we'll talk more about that later. You guys okay?
Why does X get ignored in the denominator? But
That's brilliant. Oh my goodness. Oh, shoot. Good. So, guys, can we answer Elizabeth's question? I know your butts are getting numb and the brain can only absorb what the butt can endure. But guys, can we answer Elizabeth's question and then break? Guys, her question is, why do we get rid of the X here and not get rid of the X here if that X represents the same number, right? Here's the answer. It's all about comparison. It's all about insignificant relative to what? So this minus X is insignificant compared to 0.3 molar. This X is not insignificant. So now let's talk about what it isn't insignificant to. And the answer is these X's in the numerator represent the concentration of hydrogen and acetate, but let's say hydrogen. So this concentration of hydrogen ion is not insignificant compared to the concentration of hydrogen ion, which is already present, which is 1 times 10 to the 7th molar, because that's the concentration of hydrogen ion on in the autoionization of water process. So this number is bitty compared to this, but it's not bitty compared to the concentration of hydrogen ion that just exists in the water naturally, so we include it. Is that okay? Guys, let's call timeout. We're going to come back another 5 minutes, and then we're going to get into lab. Take a break. Maybe? Ooh. So guys, deep thought number 1 is this. So let me refresh your memory. Ant spit, 4% protonated. Vinegar, 1%, 1% protonated. Guys, which one is a stronger weak acid? Ant spit or vinegar? Ant spit. It breaks apart more, right? And so guys, where do we find that information represented? We find it here. The Ka value for vinegar is 10 to the negative 5th. The Ka value for ant spit is 10 to the negative 4th. Therefore, it is a stronger weak acid. Does that make sense? Now this. Ready? Let's look at the conjugate bases. For this one, it's the CHO2. For this one, guys, for this one, it's the acetate ion. So guys, this is the logic. This is a weaker acid, yes? Therefore, this is a stronger conjugate base. Yes? Okay, let's say that again. This is, compared to ant spit, this is a weaker weak acid. Therefore, this is a stronger conjugate base. Is that okay? So guys, this then. So Ka tells us, and this you want to write down. Guys, Ka tells us the strength of a weak acid. Ant spit 10 to the negative 4th, vinegar 10 to the negative 5th. Is that okay? But then guys, we've got the Kb value for the conjugate. What is the relationship between the Ka of the acid and the Kb of the conjugate base? The stronger the weak acid, the weaker the conjugate base. Yes? Guys, all of that hinges on Kw. Find that on your equation sheet. Don't ask why. Just enjoy it. You see it there? But guys, be really, really careful. This is HA in equilibrium with A minus and protons. What we're saying is, the stronger the weak acid, the weaker the conjugate base. That was deep thought number 1. You good? Okay. Now guys, deep thought number 2. We can do calculations. You know how we did all the ice boxes for acids? Guys, find the equilibrium expression for weak bases. Do you see it there? Y'all got it? So guys, it says this. Kb is equal to hydroxide ion concentration times Hb plus all of that divided by the concentration of B. So guys, what is going on here? And the answer is this. You've got B and it is reacting with water. Then this reaches equilibrium with the products, which are Hb plus and OH minus. Why is the water not there? because it's a pure liquid. But guys, the water has to be in the reaction because that's where the OH comes from. Remember when we talked about that? That the B steals a hydrogen, the base steals a hydrogen from the water. That's where the OH comes from, and then it makes Hb+. But guys, the water is your source of hydroxide ion, so it has to be there. Is that okay? So then this. How on earth do we figure out then how to study something like NH3? You don't need to write this down, but watch. So guys, imagine this. Imagine that we've got an ice box and it tells us that we have 0.1 molar ammonia. And the question is, what's the pH? Well, guys, how would we solve this? Do you see what we're saying? 0.1, just like the 1.3 molar vinegar, what's the pH? This is now 0.1 molar ammonia, what's the pH? This is the process. First of all, put a squiggle underneath the water. You don't need it. It doesn't have a molarity. Then this is 0, and this is 0. I'm going to get rid of this down here. And then, guys, what you're going to do is go minus X, plus X, plus X, and then this is 0.1 minus X, and this is X, and this is X. Is that okay? Then you're going to go Kb is equal to NH4 plus OH minus, and then concentration of NH3. Then, guys, you would need the Kb for this. Strangely, I think it's also 1.8 times 10 to the negative 5th. Is that right? I think that's true. Hold on a second. I'm not thinking about what you're talking about. Let me look it up really quickly. Ka, Kb, NH3. Oh my gosh, guys, it is. The Kb for this is the same as the Ka for vinegar. What were you asking, Elizabeth? Well, you could figure it out, but if you did figure it out, it would look like this, where they give you the pH, and then you can solve for it. Yep. Okay. You couldn't do that. You have too many variables. You have to know one or the other. Yep. Okay. So guys, how do we solve this then? We would go 1.8 times 10 to the negative 5th is equal to x squared divided by 0.1 minus x is approximately equal to x squared divided by 0.1, and we just solve that for x. That gives us this. Then what do we do with it? How do we find the pH? So the negative, but this isn't pH, this is POH. So guys, we would go POH is equal to the negative log of OH, and that would give us the POH. But we want to know the pH. pH plus POH equals 14, and then we can come up with the pH. Good? Good. Homework. Yes?
So you can define that pH?
Absolutely. Yeah. No question. Oh, yeah. Yeah. The only thing that scares me about that is that when I start trying to cram too much stuff together, I make mistakes. I like to solve them individually. If you like to create one grand equation, that's awesome. All right, guys, this is it.